Now, what happens at theta equal to 0? So, once we have seen this formula, then we can find out some interesting cases. For example, what happens at theta equal to 0? If we put theta equal to 0, then we see that T2 does not appear. So, what happens at theta equal to 0 is that this vector OC now lies along V1 vector, right. So, which means that, say I can draw this one here, this is the vector VR here. Okay. So, what do we guess? That in order to realize this vector VR, we should only switch V1 vector and the 0 vector. These are the two vectors we should only switch, because this vector is now lying on V1 axis. We cannot switch the V2 vector here, because as soon as we give a weightage to V2, then the vector VR will start moving anticlockwise towards V2. So, it is also seen from the equation that at theta equal to 0, T2 becomes 0. So, we should not give any weightage to V2 vector, and so in order to realize this VR, we should switch V1 vector for a large duration of time, but for a certain small duration of time, as we see from the length of the VR, we should switch the 0 vector. Okay. Small duration the 0 vector, and for a large duration the V1 vector. In a similar way, if I had a vector which was lying here VR, then I must switch the V2 vector for a long duration of time and the 0 vector. We should not switch the V1 vector at all. What will happen? Let us take another example, this one. What will happen if VR is equal to 2/3 Vd, which means that if VR is this one, this is VR is equal to V1 is equal to 2/3 Vd. What does it indicate? It indicates that this throughout the Ts time period, we should only switch V1, nothing else. Okay. For the whole time period, the 100% duty or 100% of the time period, V1 should be switched, and 0 vector or V2 vector should not be switched, and this can also be understood from this T1, T2 and T0 expression. If you put VR is equal to 2/3 Vd, you will find that T1 is equal to Ts and T2 equal to 0 and T0 equal to 0. Okay. At theta equal to, so this can be also understood from this expression that suppose VR is equal to, if we say VR is equal to 2/3 Vd at angle 0 degree, then of course which means theta equal to 0. So, which means T2 will become equal to 0, and T1 if you substitute in this equation, then we see that T1 will be equal to sin pi by 3 into 2/3 Vd divided by Vd into root 3 into Ts. So, this value will be root 3 by 2 into 2 by 3 into root 3 and which into Ts, which is equal to Ts. So, therefore, we find that if VR is 2/3 Vd at an angle 0 degree, then T1 is equal to Ts, T2 equal to 0 and T0 is definitely therefore will be equal to 0. So, that throughout the time period, Ts time period, only the vector V1 will be switched. Okay. Now, as we had earlier also said, the 0 vectors are the V0 and V7. Okay. They are usually, their duration is usually kept equal. Okay. It gives the best harmonic performance. So, T0 by 2, T01 is equal to T0 by T07 is equal to T0 by 2. Say here we have seen, we have split V0 and V7 into T0 by 2 and T0 by 2 in this switching. So, but for some special switching sequences, for example, if you have discontinuous PWM, this division is not made equal. Okay. And this is done in spite of the fact it will give poorer harmonic performance, but it is done for getting some other benefit. For example, like loss distribution or changing the losses in the switch, or say in neutral point clamp converter, the capacitor voltage balancing, and so on. So, these special switching sequences are used where T0, the starting and the ending vectors are not of equal duration of time. Okay. Now, this example we have given in an additional example here, that okay, when we are switching on these 3 vectors, we have we are switching 111 for T01 period, 110 for T1 time period, 100 for T2 time period, and 000 for T07 time period, where T01 is equal to T07 is equal to T0 by 2. This we have taken already. Now, how does the instantaneous pole voltage look like? Okay. When I say that we are switching these vectors, okay, for certain duration of time, then how will the switching look like? So, here we see a switching sequence. So, when we do this switching, so let us see this switching where we are switching say from 111, 110, 100 and 000. Okay. So, there is a reference vector Vr, and we are realizing by switching like V7, V2, V1 and V0. Okay. So, V7 means 111, and then V2 is 110 and V1 is 100 and V0 is 000. Okay. So, if we realize by switching these 4 vectors, how will the pole voltage look like? When we have 111, it means that A phase, B phase and C phase, all 3 are having one state. So, which means that if this is 0, this is Vd, then Vao, Vbo, Vco, all 3 are Vd during this point of time. Next is the T1 time period. Now, here we have actually divided this whole Ts time period into 2 subdivisions, that is Ts by 2 and Ts by 2. Why we have done this will be clear when we analyze the space vector PWM with implementation using a carrier. As of now, we can say that this time period Ts is now equally divided into Ts by 2 and Ts by 2. So, this is the Ts by 2 and here is another Ts by 2. Okay. These are the two subdivisions Ts by 2. Now, in one of the subdivisions Ts by 2, so this is the total time period Ts, and in one of the subdivisions Ts by 2 we can switch say V7, starting from V7 we can switch V7, V2, V1, V0. So, this is the Ts by 2 time period, and for the next Ts by 2 time period we again switch V0, V2, V1, V7. Okay. So, we have now divided this Ts time period into two parts. So, we have seen that it has been divided into two parts. So, in the first Ts by 2 period we will switch from V7, V2, V1 and V0, okay. And in the next switching interval Ts by 2 we are switching V0, V1, V2, V1, V7. That means, in the first switching cycle we are going in a clockwise direction, and in the second switching cycle we are going in an anti-clockwise direction. Exactly why this is happening can be understood when we are doing the carrier based implementation of SB PWM. Okay. Now, you see here how will the pole voltages look like. The pole voltages, for example, in the first interval we have V7 vector, which means we have applied 1 1 1. So, during this first Ts by 2 period, if we see the first interval is T01 divided by 2, because now we have divided the whole Ts period into Ts by 2 and Ts by 2. So, we have now 4 states under 4 timing periods under Ts by 2. Those 4 timing periods are T01 by 2, T1 by 2, T2 by 2 and T07 by 2. And in the second subcycle Ts by 2 we have T07 by 2, T2 by 2, T1 by 2 and T01 by 2. So, basically we have split the whole thing into 2 parts. Now, during this, of course, here in this example T01 is equal to T07, that is what space vector PWM ensures, that the 0 vectors are equal in. So, in this Ts by 2 we see that we have a 0 vector at the start and a 0 vector at the end. Similarly, in the next Ts by 2 interval we have a 0 vector at the start and another 0 vector at the end. Both these 0 vectors are equal in duration. In between we have these 2 vectors T1 and T2 which are the active vectors. So, if we see the pole voltages we can see that 1 1 1 you have for the first T01 by 2 period, which is actually equal to T0 by 4 period, because in this example T01 is equal to T07 is equal to T0 by 2, T01 is equal to T07 is equal to T0 by 2. So, therefore, in the first T0 by 4 time period we have 1 1 1, that means VAO, VBO, VCO all 3 are having a voltage of Vd. In the next timing interval T1 by 2, so this is the timing interval T0 by 2 here, sorry T0 by 4, this is the timing interval here T0 by 4 where all of them are 1 1 1. In the next timing interval which is T1 by 2, we have 1 1 0. So, you have VAO 1, VBO 1, VCO 0. Then in the subsequent, in the third one, which is for a duration of T2 by 2, we have 1 0 0, which means VAO is 1, VBO is 0, VCO is 0, and in the last one we have 0 0 0, which is again for a duration of T0 by 7, sorry T0 7 divided by 2, which is again T0 by 4 timing duration. We have 0 0 0, which means VAO is 0, VBO is 0, VCO is 0. Okay. And next, in the next Ts by 2 period, this will again get repeated, but it will be in a opposite direction of switching. So, this is T0 by 4, then we have T2 by 2, then we have T1 by 2, then we have T0 by 4. So, this is how the switching is happening, and this is the time duration for which the switching is happening. We can note several things here. The first thing that we note is that this kind of switching is ensuring that at whenever there is a switching transition, that means whenever VAO or VBO or VCO is going from 0 to VD or VD to 0, whenever there is such a switching transition, then only one phase is having that. Okay. So, here you can see that initially all three phases are having VD voltage here, and only C phase goes down, while A and B phase is maintaining the voltage. Again here at this instant B phase is going down, while A phase is at VD voltage. So, which is evident from this 1 1 1, 1 1 0, 1 0 0 and 0 0 0. This switching sequence ensures that there is minimum transition happening, and that minimum transition is only one out of the three phases is doing a transition. Now, another thing that is important here is the switching frequency of the phase. So, the switching frequency is defined as the time for which the switch is turned. So, it is a total time period for which the switch is first turned on, it turns off and again turned on. Okay. So, this is called the switching frequency. So, here we see that the A phase, if you see the A phase here, it was, so this is during the entire Ts time period, we see that A phase it was turned on here, or I mean turned on means the upper switch was turned on, and then the upper switch is turned off here, the lower switch is turned on here, and then the upper switch is again turned on. Okay. So, therefore, the upper switch as well as the lower switch, because they are complementary in nature, the upper switch is turned on and off once in this whole time period Ts, which means the switching frequency of the upper and the lower switches in phase A is equal to 1 by Ts. Okay. Similarly, if you see B phase, the upper switch in B phase is turned on here, it is turned off here, remains turned off throughout this time, and then again turns on here, the upper switch in B phase. So, it means that the upper switch in B phase is switching once in this whole time period Ts. So, it has a switching frequency which is equal to 1 by Ts. Similarly, VCO. So, both the devices in each leg have a switching frequency which is equal to 1 by T s. Okay. So, T s is we also say that T s is the sampling period. Where is that sampling comes from, that we will see when we go into the carrier based PWM. But during this time period T s, where we are trying to realize the reference vector V r, that time period T s or this is inversely equal to the switching frequency of the devices. So, higher is the switching frequency, it means lower is the time T s, okay, or vice versa, higher is the time T s, lower will be the switching frequency of the devices. Okay. So, when you say that this was the timing durations to realize the vector V r for, so these were the, so we can say that V r, this was the vector which we want to realize. In the next time interval we can realize a vector, reference vector here, in the subsequent here like this. So, this is how the reference vector is moving in a circle. So, at each point of time we are basically sampling the reference vector and then having a switching like this and trying to realize the V r vector, the reference vector. Okay. The reference vector is rotating, for example, in a circle. So, this is the voltage which is getting impressed on the load. Okay. The load phase space vector, load phase voltage space vector is this V r which is rotating in a circle, and we are trying to realize this one using these for each time we are using this samples here. After taking the sample, we are doing the calculations from which we will be able to find out the time durations for which V 0, V 1, V 2 and V 7 or any other sector will be used. Similarly, it will be possible that for the second sector we will use this one, this one, this one and again this. So, V 0, V 0. So, the switching will be 1 1 1, 1 1 0, 1 1 1 and then 1 1 0, 0 1 0 and 0 0 0, again 0 0 0, 0 1 0, 1 1 0 and 1 1 1. So, this is how the switching in sector 2 will happen, and you can similarly find out the switching in when the reference vector is in this position, then the switching is happening in sector 2. Similarly, you can find out, for example, if the reference vector is in sector 5, then the switching, how will the switching happen, which are the vectors involved and what are their timings.